So today we're going to be thinking about amines. And one of the things that's really valuable for us to talk about before we even start is the context in which we think about amines. So here are some examples of currently used intravenous anesthetics. You can see here that each one of these compounds incorporates amines. If we think about major classes of antidepressant drugs, whether that's a monoamine oxidase inhibitor or a tetracyclic and unicyclic antidepressant, or if it's a selective serotonin reuptake inhibitor, or tricyclic antidepressants, or serotonin antagonists and reuptake inhibitors, as well as serotonin norepinephrine reuptake inhibitors, you can actually see here that each of these molecules incorporates amines. And then if we think about the chemistry of decongestants, so whether that's pseudoephedrine or oxymetazoline or phenylephrine or xylometazoline, again, each of these has this class of functional groups called the amines. So we're going to start by thinking about how to name amines. So we have primary, secondary, or tertiary amines. So these are amines in which the first, second, or third hydrogens of NH3 are replaced by alkyl or aryl groups. So take a moment, see if you can identify which is a primary, which is a secondary, and which is a tertiary amine. You can check your work. We also then further divide amines into aliphatic, aromatic, and heterocyclic amines. So an aliphatic amine is an amine in which the nitrogen is bonded only to alkyl groups. An aromatic amine is an amine in which the nitrogen is bonded to one or more aryl groups. So if we take a look, we have aniline, N-methylaniline, and benzyl dimethylamine, which is a tertiary aliphatic amine. You can see the aromatic amine as well as a primary aromatic amine. And then if we look at our heterocyclic amines, these are amines in which the nitrogen is actually part of the ring itself. So it's one of the atoms in a ring. We have pyrrolidine, piperidine, pyrrole, and pyridine. So notice we have both heterocyclic aliphatic amines as well as heterocyclic aromatic amines. If we look at our aliphatic amines and naming, we're going to replace the E of the parent alkane with amine. So take a moment and see if you can come up with a reasonable name for one of these structures. So we have 2-butanamine, S1-phenyl ethanamine, and 1,6-hexane diamine. Remember, we want to make sure that we pay attention to that stereochemistry. It's important, too, to remember that the IUPAC system also retains the common name aniline. So if we think about how we would name these compounds, right, they're all derivatives of aniline, whether that's 4-nitroaniline, 4-methylaniline, or 3-methoxyaniline. When we have four groups that are bonded to the nitrogen atom, we actually name that compound as a salt of the corresponding amine. So for example, tetramethyl ammonium chloride is a salt, or hexadecyl pyridinium chloride is a salt, or benzyl trimethyl ammonium is a salt. And it's important for us to remember that amines are polar compounds, both primary and secondary amines that form intermolecular hydrogen bonds. So if we think about hydrogen bonds and their significance, you might want to consider why the nitrogen hydrogen bonds are weaker than the oxygen hydrogen bonds. We can actually see that here if we take a look at the molecular weight and then the boiling point of these respective compounds. So what do you think? Well, although amines are polar compounds, the nitrogen hydrogen bonds are weaker than the oxygen hydrogen bonds because of the difference in electronegativity. So if we look at the difference in electronegativity between N and H and compare that to the difference in electronegativity between O and H, we actually see a pretty significant difference. So all amines are weak bases and aqueous solutions of amines are basic. I want you to think about drawing the mechanism for the reaction of trimethylamine with water. It's also common to discuss the basicity of amines by reference to the acid ionization constant of the corresponding conjugate acid. So if I had any conjugate acid-base pair, remember that the pKa plus the pKb is going to be equal to 14. If you use the values of pKa, then you can predict the position of equilibrium in acid-base reactions. So take a moment, tell me what the stronger acid and the stronger base would be, and then what the conjugate acid and the conjugate base would be, and predict the direction of equilibrium. So remember, as acetic acid is the stronger acid, therefore the position of this equilibrium is going to lie to the right. Now, if we take a look at this table and we look at the pKa's of amines, we should be able to notice a general trend. Right? Our primary amines and our secondary amines and our tertiary amines with respect to pKa. So notice that all of these, with the exception of ammonia, are going to be somewhere in the 10 range. Trimethylamine is the only other outlier. So aromatic amines are considerably weaker bases than aliphatic amines. You can prove this if you think about resonance. So take a moment, draw the products for each of these reactions, and then tell me if resonance occurs for each of these compounds. If you identified that aniline will show resonance, but cyclohexylamine will not, you're correct. And this is why we see the difference in the pKb's of each of these compounds. Aromatic amines are weaker bases than aliphatic amines because the resonance stabilization of the free base is lost on protonation. So here are two keculae structures, and you can actually see the resonance that occurs. So you have the interaction of the electron pair on nitrogen with the pi system of the aromatic ring. This reduces the availability of the electron pair to participate in a reaction with acid. Electron withdrawing groups such as halogen, nitro, and carbonyl are going to decrease the basicity of aromatic amines by decreasing the availability of the electron pair on nitrogen. So if we think about the reduced availability of the electron pair on nitrogen to be able to participate in a reaction with acid through the inductive effect and a resonance effect, then we can actually quickly see why we see a significant difference in the pKb of aniline versus nitroaniline. So take a moment and decide which is the stronger base. It's also useful to think about guanidine. So this is the strongest base among neutral organic compounds. I want you to think about drawing 3 resonance delocalizations of the positive charge over the 3 nitrogen atoms. So how would you draw resonance for this guanidinium ion? If you identified that its basicity is due to the resonance delocalization of that positive charge, then you were able to show the 2 arrows indicating the movement of electrons for these compounds. You'll quickly notice that these are 3 equivalent contributing structures. Finally, all amines, whether soluble or insoluble in water, are going to react quantitatively with strong acids to form water-soluble salts. So, for example, if I have R-norepinephrine, which is only slightly soluble in water, and I expose it to HCl, it's going to form the hydrochloride salt, which is a water-soluble salt. This is one of the ways that we're actually able to solubilize and absorb chemical compounds that are frequently used as drugs. So the last thing we're going to look at is the reaction of an amine with an alkyl halide to form a new covalent bond. So we're going to look at the role of a nitrogen as a nucleophile. It's going to react with an electrophile, so a carbon. Remember, again, chloride in this case is our leaving group, and we're going to form a salt. Now, it's important for us to think about the fact that you can remove that proton and actually convert the salt back to a free amine. So in step 2, essentially you're producing a new secondary amine, which can act as a nucleophile. So there's going to be a varying ratio of each of the different types of amines that are possible to form. And these ratios are so difficult to control that you really generally want to avoid using amines as nucleophiles, particularly in nucleophilic substitution reactions, because you will always see a variety of products. So the next time we talk about content, we'll be looking at aldehydes and ketones. Thanks again. Have a great day.